For the moment, coal represents no problem. Production should increase by around 25 million tonnes a year to 150 million tonnes, at which rate it should last around 300 years. But the production of North Sea oil will peak as early as the 1980s. It'll help our balance of payments problems by being exported between now and the 1990s, and then it'll begin to run out by the turn of the century, dwindling to nothing. Natural gas, in economic terms, will also start to disappear by the turn of the century. But will our enormous coal reserves make up for the loss of oil and gas? Remember what Dr. Marshall said, that coal may soon be too valuable to burn because it'll have to be used to produce gas, plastics, even petrol. Remember, too, that Britain is using more and more energy. And as our demands rise and our fuel supplies dip, with the shortage of oil and gas, alternative forms of energy must be found to fill the energy gap that will emerge in the 21st century. Dr. Peter Chapman.
It could be that with energy conservation, small contribution from solar and waves, and a moderate-sized nuclear power programme, we'd be comfortably off for energy by the year 2000. But at that time, the oil and gas supplies would be running down, and we'd be looking for a substitute.
So, if the right decisions aren't made now?
If the right decisions aren't made now, then we would find ourselves in trouble shortly after the year 2000, without any doubt at all.
3 years ago, Britain took a trip in a time machine. We all had a foretaste of how bad things could become when oil supplies begin to run out. The oil-producing countries pushed up the prices and cut supplies, and motorists queued for whatever petrol there was. If there's going to be an energy gap, where will it appear? By far the biggest share of our energy, 65%, goes into the creation of heat. Electricity, coal and gas to heat shops, homes and offices. Then there are the transport fuels to drive cars, trains and aircraft, 15%. And then there's electricity for use in domestic appliances and industrial production, 20%. There are now 11 first-stage nuclear power stations in Britain. All are burner reactors, that is, they burn uranium. In addition, there are now 5 second-stage nuclear stations. They're called Advanced Gas-Cooled Reactors, AGRs. But only 2 of the 5 are working, and these are years behind schedule. 20 years ago, nuclear power was presented as the answer to all our fuel problems. It hasn't quite worked out like that. Dungeness is typical of the problems that have beset the nuclear industry since the early 60s. This monument to nuclear bungle is 8 years behind schedule. It's costing 3 times as much as was estimated. That's £200 million over budget. And so far, it hasn't contributed a single spark of electricity to the national grid. Nor is there any guarantee that it ever will. Dungeness is one of Britain's second-stage nuclear stations, an AGR. The fast breeder reactor that Dr. Marshall was talking about is a third-stage nuclear power station. Even more costly, even more difficult to perfect. So difficult, in fact, that no one in the world has yet made a commercial fast breeder nuclear station that works. Dr. Marshall talks of a minimum of 150 nuclear power stations in Britain by the year 2025. Now, the lowest estimated cost for building one of these stations is £800 million. So to build 150 fast breeder stations would cost at least £100,000 million. And that's on today's estimates. And we still haven't made one that works, nor have we solved the safety problems. So shouldn't we be looking more closely at alternatives that are both potentially simpler and safer? In a laboratory at Edinburgh University, Stephen Salter has been working for the past 3 years on a machine designed to harness the power in the sea. It's been nicknamed Salter's Duck. It's estimated that 300 miles of Salter's ducks are capable of supplying all Britain's peak winter electricity. This machine can extract 90% of a wave's energy. The research costs just £40,000 a year. Salter hit on the shape of the duck because the motion inside a wave is circular. As the waves move forward, the motion lifts the nose of the duck, and it's this that provides the energy that's turned into electricity, as it drives a series of generators inside a whole line of ducks. The electricity will then be carried ashore by cable. But unfortunately, the sea isn't like this. I mean, it's not regular waves, calm under laboratory conditions. Have you actually tested this machine under simulated sea conditions?
We're just starting to do that now. Jamie, could you put on 20 knots Pearson Moscovich? Okay. Now, this is a good deal more realistic. I think cut the smarts as well, perhaps.
So that's quite a rough sea.
Medium in the Atlantic. Medium in the Atlantic. And we can measure the efficiency of this one. The first time out, we were down to about 55 in these conditions.
55% efficiency?
Yes. Now, ideally, the overall final efficiency ought to be somewhere between 40 and 60.
These ducts will eventually be 40 feet high and made of concrete. Maintenance will be expensive, but there's no radioactivity nor risk of explosion, and the fuel, the waves, is free and inexhaustible. Stephen Salter has done his sums.
It depends solely on the economics. The trouble is that your other motivations, however sincere they may be, don't necessarily impress the people who have to make the decisions. Doing it for the right money does impress them. And I think that that is really the best way to win, to beat people on price and delivery.
Stephen Salter already knows where he wants to put his 300 miles of ducts. It's here, off the northwest corner of Scotland. That'll be sufficient to meet the average winter demand for electricity in the whole of Great Britain. Unfortunately, most of the electricity will be needed in the industrial heart of England, and to get the power there will cost more money, a fact that Salter's included in his estimates.
You'd need a substantial amount of backup, but we already have that. I mean, we've got an enormous amount of capacity at the moment. The times we'll need it will be the times of the lowest demand, and no single technology can give you 100% reliability.
And there is plenty of backup available. Even today, we can produce 50% more electricity than we need. How optimistic, then, are you today?
I think I would give it a 50-50 chance of contributing a fair bit by 1990. I think we could be beginning to really take the strain of the bulk of the electrical supply, if necessary, after that time.
There are a lot of institutional pressures to continue the nuclear power programme, and certainly the fact that an awful lot of money has been spent on the research and development means that there is a financial pressure. But I would suggest to you that the institutional pressure is probably even larger. The large number of research scientists, of administrators, the Nuclear Power Construction Company, the United Kingdom Atomic Energy Authority, the interests of the boiler makers, the turbine manufacturers, the civil construction business, all these people have a financial and vested interest in seeing a nuclear power programme, and they represent a very strong lobby, as indeed they should. And we're likely to find that we have some nuclear power, regardless. The question really is how much can we afford, and how much do we need?
Which were three of the questions considered by the Energy Conference this week. But is there a viable alternative to the all-out drive for nuclear power? Walter Marshall, Chief Scientist at the Department of Energy, thinks there isn't.
Not if our life is going to stay roughly as it is now. It would have to, if in fact we abandon nuclear power or reduce our dependence on it substantially, life would become quite uncomfortable in many ways. It would become quite different. We'd have to change our lifestyle.
We've been putting all our eggs in one basket, which is the nuclear basket. Now, we can't afford to get all our energy from the nuclear source. And in fact, if you look into the future, you find that there is the potential to get part of our energy from a wide range of needs. Put crudely, if we can find 10 different ways of getting 10% of our energy demand, then we're home and dry.